You need to listen. You need to listen intently. There's something I need to share. So, a very famous mathematical equation, okay? So, it's that the summation from n is equal to 0 to infinity of 2 raised to the n. This is equal to 1 plus 2 plus 4 plus 8, doubling every single time you add, plus dot 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 forever and ever and ever, is equal to negative 1. Now, I know what you're thinking. That makes no sense. But it does. It does. I need you to think about this for a second, okay? So, imagine you are tasked with building a computer with an infinite resolution of bits, and you need a way to represent negative numbers, okay? So, what you might want to do is, well, you couldn't add a negative number to, for example, you'd have a bunch of zeros, right, forever and ever and ever, trailing a number like 1, 1, which would be the binary equivalent of 3. And you can also add in decimals, which would be, if you add in 1, 1, this would be 0.75, because this one represents 0.5, and this one represents 0.25. So it doubles as you go to the left, and it halves as you go to the right. Now, I want you to think about something. What is negative 1 plus 1? Right? Think about it. 0. It's 0. So, if negative 1 plus 0, if negative 1 plus 1 is equal to 0, that means that we need a binary number that's, keep in mind, we can't have a negative sign here because there's no way a computer would be able to register that. In finite computing systems, we just say that the last bit, the most significant bit, is negative, and that's how you can add signs to integers, floats, whatever. But we have an infinite number of bits in this case. So, hear me out. If we have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, forever and ever and ever, extending all the way to infinity, this is your 1's place, this is your 2's place, this is your 4's place, 8's place, so on and so on, doubling every time, you get back to this formula. It makes sense. Now, what happens if we take this number? Where's my eraser? It's here somewhere. Eraser. God, where did I put it? Come on. No, it's here somewhere. Okay. I don't know where I put my eraser, but it doesn't matter. Here, I'll just erase it. What happens if we add 1 to this number? This number, as we have stated, is equal to negative 1. It is equivalent to negative 1. What happens if we add 1 to both sides? Well, 1 plus 1 in binary is 1, 0, so that carries the 1 over here. 1 plus 1, 0. And then we carry the 1, 1 plus 1, 0. And we do this forever, and we have an infinite trail of zeros. This number, an infinite list of numbers going all the way to the left to the largest possible 2's place, is eventually going to be negative 1. Now, this is crazy. This is insane. However, and even sorry, I am rambling, but this is also how we define what's called 2's complement. So that's pretty fucking incredible. However, there's something else. There's something else that we should take into consideration. What about binary numbers, as I said, with decimal values, or with a fractional values? Well, 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16, having every single time forever eventually is equal to 1. So this leads us to a conclusion. If you have 1, 1, 1, 1, 1, 1, 1, 1, 1, forever and ever and ever, extending all the way to the left, 1, 1, 1, 1, 1, 1, 1, 1, 1, extending all the way forever to the right, this is equal to 0. How? This means that an infinite sequence of 1's is equal to an infinite sequence of 0's. And this is mathematically consistent. Watch what happens if we add 1 to this. We go plus 1. This becomes a 0, 0, 0, forever and ever and ever. This 0.111111. As we said, this summation right here would come out to 1. This is mathematically consistent. Okay. And there's other ways of proving this as well. Take, for example, 11111, forever, never, 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 extending all the way to the left, right, times 10 in base 2 plus 1 is equal to 111111111. Now we're going to call this x because let's say we don't know what it is. We don't know what it is, right? Sorry, this is 111 extending forever. You get it. These are the same thing. These are x. So we get x times 2, because 1 0 in base 2 is 2. 1 0 in base 2 is 2, right? 2x plus 1 is equal to x. Subtracting 2x from both sides, we get x is equal to, or negative x is equal to 1, or x equals negative 1. It works. But how can an infinite sequence of 1s be equal to an infinite sequence of 0s? It doesn't make sense. But it does make sense because it's mathematically consistent. Okay. I mean, there has to be a rationale here somewhere. But where? And here's the thing. Does this apply to other bases? Could we apply this to base 10? Or base whatever, base 10, base... Oh my god, we could. In base 10, hold on. So, in base 10, if we have an infinite trail of 9s, this must be equal to negative 1. Think about it. Applying the same reasoning, if we add 1 to this, this becomes 0, 1, 0. Oh my god. Math is broken. We can't have this. What? It doesn't. I don't know what to make of this. Somebody help me, please. What is this? What does this mean? Why is it consistent? Why does it work? Please.